Let's start. So our next speaker is Lilit Zargaryan from ServiceTitan, and the topic is MLOps, which is one of the most important and maybe overlooked topics, because it is not enough to train a model on your computer, on your notebook. It is really important to get it working. And this talk and the next talk will be about actual production issues which companies face and have to solve to get machine learning actually bring business value to
I'm Lilit Zargaryan. I'm working as a machine learning engineer. ServiceTitan is the world's leading audio software company for trades. My past experience was I have 3 years experience in data science, and as long as we have started to work on machine learning platform creation, I have switched to the machine learning engineering role, and I don't do that. Today's presentation, although these all topics can be a matter of long-hour discussions, today's presentation goal is not to do that. It's to give the bird's eye view on the knowledge you need to know to advance your machine learning infrastructure, or the possible steps you need to do it. So let's talk about a bit MLOps. So MLOps, we have a goal to reduce time from analyzing the problem, creating model, and deploying an actual solution, but maintaining the quality of the output. In software engineering, this approach is DevOps. So we can borrow the term and in machine learning say that it's MLOps. We can think of MLOps as a lifecycle management discipline for machine learning. Some of the concepts from DevOps directly translate to the MLOps. And here are the concepts: continuous integration, continuous delivery, and continuous training. So in the software packages, we can rely on our software working every time we run it. But in real world, machine learning, as the data changes, machine learning models go off, and the data inevitably changes. So we need to introduce new term, which is continuous training. Continuous training is is set up from the steps monitoring, measuring, retraining, and serving. And there is another concept to continuous integration. There is another specific key in the MLOps, and it is that continuous integration is no longer about testing the code and its component. It's about testing data and models. And continuous delivery, we are not delivering just a software package, we are delivering whole machine learning system. For example, we're delivering machine learning training pipeline, which is a service, and this service itself creates another service, which is the model instance, and it actually gives us predictions. So, before starting to advance your machine learning system, one should think of where its machine learning stands, and there are different levels of maturity of the machine learning system, and this maturity is defined by the automation steps. The basic level of maturity is level 0, and it means that the company is doing deployment, building models manually. In the summary, level 1 just have continuous training enabled, and then level 2 have automated training, evaluation, and deployment. Here are the recommended steps from level 0 to level 2. It actually kind of we follow this structure in our presentation. cloud, the first step you should do to automate your machine learning workflow is to create a template project. If you don't have a template project and you may want to consider having one, it's just a basic example of this template project. Contains from the code, from pipeline definition and config files. Please note that the pipeline definition is fully automated and is changed on the config file. So here we have three example pipelines. One is the data preparation, another one is model monitoring, and the other one is scoring. So data scientists should not change anything here. They're changing the config files. For example, they're including one more feature or turning off that feature, and the pipeline will work automatically. The model training relies on the training script, which is here, and the pipeline changes when the model training script changes. And we have scoring, which is also fully automated. It's the pipeline deploying scoring script. Here are the custom non-modifiable steps. So after creating a project from this template, data scientists work on this code. There are predefined pipelines, and we can build a CI/CD pipeline. Here's the proposed architecture of MLOps platform. We have two main concepts here. One is MLOps solution, and the other is machine learning project. The MLOps solution concept is introduced as we may have different approaches to solve the business problem. Let's describe this concept. So, MLOps solution is for the business problem. So, for example, the business or production wants to give scores for the to categorize call out audio recordings. So there is one solution, and they want a machine learning solution for that. We are creating one service for that solution, and it's machine learning MLOps solution. Each MLOps solution can have different models, and it is different approaches. Different data scientists can work on that. You can have solution for the business problem and then revisit it and add a project to that. Another solution knows how to give scores for that problem. And in the MLOps context, score really means inference, not the score that data scientists think. And it knows how to monitor and how to compare these different projects. Machine learning project only exists in the concept of MLOps solution. So it should exist, it should give some solution to the business problem. And machine learning project actually has a scoring training code that creates a model instance, which is the model that is trained on the data and the scoring. So when keeping this architecture, we can cover those use cases. So single model is the basic approach. There is one approach for the business problem, and there is a single machine learning project for the solution. And what solution scoring could do is to defer scoring to project scoring code. There is another architecture for the solution, which is champion challenger. There is one main machine learning project, which is called champion, and you are adding new project to challenge that solution. So what machine learning solutions scoring does, it just defers the computation to champion's project scoring code, but monitors all the models, monitors both champion model and the challenge model. And the more extended variant of the champion challenger architecture is A/B testing. We can implement A/B testing in this architecture. The solution scoring code will first randomly select the model and then defer computation computation to the randomly selected project's scoring code, and the solutions monitoring code will calculate KPIs for all models. So you remember the template project, and we have pipelines. Now is the CI/CD pipelines built on top of our platform. Here you see the machine learning solution for this problem. For example, you want to predict the credit default score. You're adding two models. One is the basic model, and the other is challenge. And these two projects have two pipelines. One is deployment pipeline. Whenever you are, you can implement it in different ways. We have implemented it as is. Whenever you are pushing your code to your main code base, the deployment pipeline is working. So all the images, all the pipelines are created in these steps. And after that, you are running a single endpoint, which will, by triggering which, you will have your model instance deployed. And this is called training. In the CI/CD pipeline, it is called training pipeline. You are triggering training pipeline, and after that, you are getting your model instance. You can revisit it, you can change data inputs, and with the same code base, you will give another model endpoint. So code and configurations give you the project version, and when you're adding data to it gives you the model instance version. This is the single model architecture here. And enough about this platform, enough about our solution and machine learning project platform. As the machine learning infrastructure has matured, there is a need to monitor our models after deploying to production. And it's a pity that there is no actual playbook for the teams that guides us to kind of systematically monitor our models. We're proposing template for that playbook. Actually, the data flow of monitoring is as this. The model features come. There is a model that stands for the business problem. You are generating score predictions, and you are persisting your outputs in the scoring repository. Please note that for every single entity that you are giving prediction, you should have an object ID. That will give you the opportunity to then match it to the real target score. After some time or immediately, there is an event, and actual ground truth data is collected. You are generating target value and keeping these values in the target repository under another table, but they should share the same ID. After you have your score persisted and the target value persisted, you are matching these scores. You are calculating performance, and the logic of calculating this performance is written in your MLOps solution monitoring report card. And you are in some dashboard or logs, you see that the performance of your model is increased or decreased, and you are setting up some alerts for that. This is the basic data flow, and this is the target detection mechanism. You can have on-request collection of the target, you can set up jobs or rule-based jobs to collect your targets. It seems really straightforward, and there is no problem in this flow described, but actually the target detection is really the most difficult part for the monitoring after the deployment, and we're describing some use cases of the target availability. The first case is when when you have your ground truth in real time. So this is the ideal scenario. businesses are lucky enough to have this scenario. For example, it's in the case of digital advertising, you're giving prediction that the user will click on this ad, you're showing the ad, user either clicks on that or not, and you will have in a matter of milliseconds that the actual value of your ground truth. The other case is delayed ground truth. So you don't have your ground truth in real time, and depending on how long will be the lag from your prediction and the collection of the ground truth, it's a big problem of that. If the delay is significant and your model needs to have real-time monitoring, we are suggesting to use proxy metrics. For example, you are giving prediction for the loans. You are giving prediction whether to give a loan to some person or not. So until that person does not pay out his loan or go default, you will not know if your prediction was right. So you can have a proxy, for example, the late payment dates, and start to monitor it. For example, the percentage of the customers that done the late payment, and that will give you the sense, of your model's performance. And one more thing to consider here: for some cases, there is a fixed time, at least the maximum time that you will know that the ground truth will come. But there are cases that, for example, you have given the prediction that this transaction is fraudulent until the customer reports that their credit card was stolen. You will not know that your prediction was true or not. So that enhances the need for proxy metrics. The other case is the biased ground truth. In this same example, you have given the loan to some customers, and you don't know the actual values for the customers whom you have denied. So you should keep in your mind that your ground truth is biased. The solution for this is to create a hold-down set and give loans to everyone, regardless of what your model performance said, and you will kind of decrease this bias in your ground truth. And the worst scenario is when you don't have any ground truth in the environment. So again, the solution is to use proxy metrics. A really good proxy metrics that correlates with your target data can help you to have a sense of your model performance in real time, and you can hire your human annotators and labelers. And please note that whenever human annotators are annotating, the annotations can go directly to the scoring repository, and you can monitor your model's performance and the human annotated scores in the like you have done it in the real ground truth case. So that is one more advantage of the Close architecture, and actually Drift is a proxy for performance. In the case when you don't have real-time ground truth, you can check the distribution of your predictions, and when that distribution changes, it can alert data scientists that in real world model kind of behaves in a way than it was in the structured phase. And additional performance monitoring considerations. One is to have granular monitoring. Don't have one metric for whole model. Have it for different cohorts. For example, for different states, and you maybe in real life your model is really bad predicting for different places, for different states, and that kind of stuff. So you should do real granular monitoring, and that will give you the information to develop more robust models. after that, and the other consideration is to identify patterns whenever you're monitoring. So when you have bad predictions, it does not mean that your model is actually bad. You can kind of see the pattern and have more information about the performance. For example, whenever it's a recurring pattern, you will know that it's a seasonal thing, that your model gives really bad prediction, for example, on winters, and you can bring back your model and experiment and enhance your model prediction on that kind of seasons. Whenever it's sudden, it means that something really bad happens, for example, COVID-19 or financial crisis, kind of stuff. And these pretty much sums the steps that you should consider before doing monitoring. And another main concept of MLOps is the feature stores and what it stores. The really changing point, mind-changing thing while considering to have feature store or not is to think of feature store as a service, not as a storage. So it's a software package that enables models to give features. It's not as it can store data. It's one feature of it, but it can be solely online storage, and it's a service. So key benefits of having feature store and when this approach pays off. So main benefit is to develop knowledge base. So you're kind of reusing the features created by the previous data scientists, and you're having stability. For example, when one data scientist says have this revenue, they are predicting revenue, and the other one says that they are predicting revenue better, if you have feature store, you will know that they are talking about the same revenue. So the calculation of revenue is written in one repository. The other thing is security. So what we're doing, we have a data warehouse. We're writing the code. We are creating features on that data warehouse. We are training code, and in the inference phase, we are rewriting this code, and it's really difficult to keep these two codes synchronous. So it can lead to the risk of train serving skew. The other benefit is the quality. You will have fewer ETL because you can reuse the work done by the other data scientists, and you can set up quality control on the ETL level. And I think it's the last benefit here in the slide, but I think it's the main benefit. It's the separation of ETL from the rest of the machine learning pipeline. So you're separating your data pipelines from your machine learning pipelines, and it prevents vendor locking. For example, your company is using Postgres SQL, and you have hundreds of models, and they all rely on this Postgres SQL. Whenever they are migrating their database to another database, for example, SQL, you will have to bring all your models from production, rewrite ETL data pipelines, and redeploy. Whenever you have your feature store, you will go and change the feature definitions there. So here it kind of resembles to the concept of ORM in the software engineering. It creates an abstraction layer from the data sources. And actually you can connect to different data sources. So before starting to kind of research which feature store which feature store service you will use, or maybe you will build in-house feature store, you should identify the feature categories. There are basically two kind of feature categories: online features, for example, user inputs or obligations on that. User inputs it's the features you will have on the time of prediction, and offline features, offline raw features, and offline related features. So I think there is different setup and deployment flows for these, but I want to go to the Q&A because we have 5 minutes. So if you have any questions, we'll be glad to answer them.
Could you elaborate on what you mean by raw features for the offline?
I'm sorry, please.
Could you elaborate on what you mean by raw features for the offline model? Yeah, that's it.
Yeah, for example, you are giving the prediction for the job value, and you know that this job and this tenant has this size and that kind of stuff. So it's the features persisting in the database. And you can actually calculate the related features on top of that. So they are the features that are kept in your production database without any applications.
So, first of all, thank you for the talk. And then, do you have any kind of version design of models? If you do, can you just... and so if you do, what kind of strategy do you use? As far as I know, for example, MLOps use incremental approach, so you could just update your model, you just up one number and you get your model out of the way. If you use what kind of strategy and where it is used? I mean, do you use rollouts or something else?
Thank you for your question. Actually, I've said that we have for every model we have machine learning project, and our model instance version consists of 2 parts. The first part is the project version, and the second part is the time is the training time. So you have the version for your project. It kind of stabilizes the version for the code, config, and changes. And whenever you are doing one more training, you have your model instance version. So every time you have a version of your project, and it's here we are having that version with git commit because it's Unity identifies the version of your project, and whenever you are doing more training, you're incrementing your model version.
So it's done by the tool you are using?
Yeah. You can go back and see with which code it was trained and with which data it was trained.
Can you talk a little bit like which tools you are using and what you will use? Like, for instance, for CI/CD, do you just use like Travis or CI, or is it something specific for example? And also, do you retrain the model every time for the continuous improvement, or it's reused?
No, I'll go both sides. For CI/CD, we're using TeamCity. It's kind of the choice of the company. We're just using it. For the workflow management, we're using Azure Basics, Azure ML, and but it's actually our cloud is Azure. That's why we're using Azure. There are 2 competing services now. It's SageMaker and Azure Workspaces. Actually, SageMaker is kind of one step ahead because it has built a feature store for 3 months before. I don't know the exact date, and they have implemented the solution. SageMaker is kind of one step ahead, and for the scoring its function is really minimal. It's just the first definition from the solution to project. So the stated functions are really enough. For all the pipelines, we are using Azure pipelines. So for version control, it's Git.
Questions?
Let's